So let's start with where we left off yesterday. So the last sort of lecture and a half, I showed you typed closure conversion, and then we used a logical relation yesterday to essentially show, though we didn't do the proof, to show the correctness of closure conversion. So now let's start by talking about this cross-language logical relation approach to proving compiler correctness. All right? And now, actually, before I dive in, let me just sort of say one thing that I said 2 lectures ago, just to, because that was a while ago. This whole idea of being able to use a cross-language logical relation that relates a source language and a target language, and using that to prove correctness. The proof that I showed you yesterday actually goes back to a 1996 paper, and the idea that you can use logical relations to do correctness of translations is something that's been around for decades. But these days, whenever we talk about, using a cross-language logical relation to do compiler correctness, we normally point at a paper from 2009, which is due to Nick Benton and Gil Her, because they were the first ones to do a mechanized proof of a more, realistic kind of language. They had sort of realistic. They had a simply typed lambda calculus with recursion, which they were compiling to an SECD machine, and this, in 2009, was their response to, look, CompSer does whole program compiler correctness. Let us show you another way that you could do compositional compiler correctness, so that you don't have to make this whole program assumption. So we normally go back to that paper. And then that was followed up in 2011 by another paper, which is called a Kripke logical relation between ML and assembly, which basically takes a more ML-like language, so simply typed lambda calculus with references, polymorphism, and does a one-pass compiler to assembly. Okay? Now, both of these were one-pass compilers, and I'm going to talk about that in a minute, because the question of how do we scale this to multipass was sort of left open. Okay? And the Pilsner paper that I showed you on my linking line a couple of days ago, the Pilsner paper from 2015, was a response to how do we scale this sort of cross-language relation idea to doing compiler correctness from multipass compilers. All right? So that's the sort of landscape. Okay, so let's talk about this cross-language logical relations for compiler correctness and a couple of important problems that they have. So here's problem 1. Let's see. So what have we proved? Essentially, if I have a source program ES, now this is a component, and I mentioned yesterday that when my components can have free variables, that's when I think of them as open programs, right? I can plug in something for that free variable. So my ES up there has a free variable X in it. That's where you can come in and link in some code of your own. That's basically my mental model. All right, so I'm compiling a component ES to a target component ET, right? And then the compiler correctness proof we did yesterday essentially shows that ES is cross-language related, logically related to ET, right, in that environment. That's essentially, that captures the kind of theorem, the fundamental property that I put on the board by the end of yesterday's lecture, right? So let's assume we've proved this. Now let's look at what it gives us. Okay, so just to sort of peel away the layers, inside this logical relation, the way that we have specified compiler correctness is essentially to say this. Oh, I'm sorry, this should be, instead of ES prime and the purple ES prime, those should be values. So, but we can treat them as expressions, it doesn't really matter. So if you give me a blue ES prime, and that should be a purple ET prime, and if they are logically related, then I can plug them into my compiled components and I will get logically related whole programs. That is what that definition is telling us, right? This is what we saw yesterday. Okay, now, so let's look at this scenario. Now, you take a component ES, you compile it to ET, and you have proved this theorem, so we have that statement up there. ES is related to ET. Now, you come along and you give me an ET prime, and you say, here, go ahead and link with this. So my question for you is the following. Oops. What? Okay. How do you answer this question? Does the compiler correctness theorem permit linking with this ET prime that someone just gave you? This other target code. Now, think about this, right? This target language could be assembly. I just told you about a paper that compiled from an ML-like language and one pass to an assembly-like language. This target program, this target language can be assembly. So someone has come along and just given me some assembly code and said, go link with it. How do I check whether my compiler correctness theorem, the formal statement, allows me to link with it? If it comes from an ES prime. Okay, yeah, so I mean, in order to even answer that question, we have to say, well, what does the compiler correctness statement say? And there's my compiler correctness statement there for you again, right? What does it say? It says that if you can give me an ET prime and show me that it is related to an ES prime, then you are allowed to plug them in. Okay, so what does that mean? That means that you have to, if someone gives you some blob of assembly code, you have to cough up an ES prime that corresponds to it, right? Then, what else do you have to do? You have to show that this ES prime that you just came up with is logically related to this ET prime that someone gave you. Only once you've done both of those steps can you say that, okay, you have a whole program, I can plug these things together and I get equivalent source and target programs, right? Okay, so this is not really feasible in practice, right? You need to come up with an ES prime. If someone just gives you assembly code, how are you going to do that? Unless you already have the source code that it was compiled from. I mean, if you sort of sit down and start trying to come up with the ES prime from scratch, that's going to be tough, right? So it's not practical. And the other issue here is that you can't link with any target code, with any ET prime, whose behavior cannot be expressed in your source language S. Okay? So that's the limitation. And what I'm trying to sort of get across to you is the way to sort of, arrive at what are the limitations of the theorem is to carefully inspect the theorem and say, how do I use this in a practical scenario, right? Okay? All right. There's a second problem with cross-language logical relations, which is the one of multipass compilers, scaling to multipass compilers. Suppose that I have a two-pass compiler. I compile from a source language S to an intermediate language I. And then I compile from my intermediate language I to my target language T. All right, so I have two passes. For each pass, I'm going to use a cross-language logical relation. For the first pass, I'm going to use an SI relation. For the second pass, I'm going to use an I and T relation, right? Two different cross-language logical relations. I'm going to use these and show the correctness of each one of these passes. But then what I'd like at the end of the day is an end-to-end compiler correctness theorem, right? So at the end of the day, I want to show that my first ES, which went through 2 stages of compilation and got compiled down to ET, is in fact logically related to ET. So the question becomes, can we show this sort of transitivity property that justifies building verified multipass compilers by focusing on one pass at a time, right? So you need this sort of transitivity property. This is referred to as the multipass problem, transitivity property, etc. Also vertical compositionality, because you're trying to compose two passes together. Okay, so, yeah.
Maybe you know like this, but
yeah.
How is this a problem in the same sense that the first one is a problem? Because it seems like the first problem is kind of like outside the scope of what we're talking about with these logical relations. Like, the source language just can't express it, you're kind of screwed.
Yes.
But this seems like maybe it works. I don't know.
You're kind of right, actually. And let me tell you why. Or you will see why in a little bit. What you're sort of suggesting is that maybe we can do a lot of work behind the scenes in order to prove this transitivity property holds. That's how I'm reading your comment, right? And you're right, you're spot on. And what I'd like to sort of focus on is how much work. When is it possible, when is it not possible? And it depends on what kind of cross-language relation we have, okay? So just hold that thought for a couple of slides. All right, so what I want to talk about for a second, remember on the last slide we had a cross-language relation. All of these relations, it's an S and I relation, then an I and T relation. We're trying to compose them to show that we get a relationship between S and T. How do we normally do transitivity in a single language, with a single language logical relation, like the one that we did yesterday for simply typed lambda calculus? So normally if you're in a single language logical relation, now this is one single language on both sides. So if you have E1 related to E2 and E2 related to E3, we would want it to be the case that E1 is related to E3. And the way that, the technical way that we normally do transitivity proofs for our single language logical relations is the following. we prove that we've constructed a logical relation that is completely equivalent, has an if and only if relationship, with the normal definition of contextual equivalence for the language. And I showed you the definition of contextual equivalence for our single language yesterday, right? Okay, so you say that the logical relation precisely captures contextual equivalence for the language. Contextual equivalence, the definition is, it's trivial to prove that it's transitive. Proof is like a one-liner almost. And therefore, since contextual equivalence is transitive, it must be that the logical relation is transitive. This is how we all do these proofs. Because it's very simple, you don't have to do a lot of the actual labor of going through proof cases, etc. I've done one of those proofs from scratch back in 2006. There's a detailed tech report about it. They're just long, so you don't want to do it that way. You want to do it the easy way. Okay. Well, they're long for languages with certain features. I did this for a language with recursive types. Okay? I don't do it for languages with richer features. When you have things like mutable references in your language, and you need to prove that your logical relation is transitive, you show that it corresponds to contextual equivalence, and you say, okay, since that's transitive, my logical relation is transitive. Okay, now, let's see if we can take this insight and try to understand what happens with, so here's my idea. Transitivity for a single logical relation, we get it by proving that the logical relation corresponds to contextual equivalence. But remember how yesterday I told you that this is a cross-language logical relation. There is no definition of contextual equivalence, right? There are no contexts. On the right-hand side, I can plug that ES component into source language context, source language programs. On the other side, who's right and left, I can't. On the other side, I can only plug it into target level context. So there's no single context that I can use for both sides to plug them into, which is what contextual equivalence does, right? Okay, so there's no definition of contextual equivalence we can use. So that means we have to do essentially what you were just, sort of asking about. You have to do a brute force proof, all right? And these brute force proofs are not always possible. Now it starts to depend on what are the features in my language that I've built this logical relation for. And it turns out that these logical relations, which are able to handle things like recursive types and mutable references, ML-like languages, basically, we call them step index, Kripke, possible worlds, logical relations. In the presence of references, you cannot prove these logical relations transitive. So if I set up a cross-language relation for an ML-like language, I won't be able to prove transitivity. And the paper that I mentioned from 2011, a Kripke logical relation between ML and assembly, it was a single-pass compiler because it couldn't be a multi-pass compiler. All right? They weren't able to prove it. All right. Now, so that led to this follow-up work on something called PILS, parametric inter-language simulations. All right? This is work due to Gilher and Derek Dreyer. And they said, well, how can we take these logical relations and start to sort of scale them so that we can get these transitivity proofs? What do we have to do, technically, to the machinery to get this to work out? And so basically, long story short, with step index Kripke logical relations, you can't prove transitivity, in the presence of references at least, for these cross-language relations. But with PILS, they're inter-language, right, cross-language. You can prove it, but it's a lot of effort. Okay? All right, so yes?
Could you build a notion of equivalence between contexts, like logical relation between contexts?
But if you do, you'll still have source context on one side and target on the other, right? You need one context on both sides. If
say that you have two related contexts,
but then all you're doing is you're lifting the notion of logical relatedness to logically related contexts, but it doesn't help. There's still the beauty of the definition of contextual equivalence, it says for all C, if I plug E1 into C, that terminates if and only if, right? It was E1 is contextually equivalent to E2 if for all context C of a certain type, C with E1 terminates sort of if and only if C with E2 terminates, right? This is, if you line up two of these, E1 is equivalent to E2 and E2 is equivalent to E3, it's trivial to prove transitive, but you can't do the same trick with when you don't have a single context spanning the E1, E2, and E3. That's the problem.
So could you just remind me what PILS stands for?
Okay, parametric inter-language simulation. So I've been saying cross-language. They called it inter-language, easier to pronounce in an acronym. Okay, so the word simulation kind of replaces logical relation. The inter-language captures the cross-language part, and they're parametric in a certain amount of knowledge, which is the whole trick on getting them to be transitive. Okay, so here's the bottom line. PILS solve this problem of cross-language transitivity, right? So they solved the multipass compiler problem in a sense. But the issue is that the first problem that I showed you still remains, right? This issue of if you give me an ET prime, what do I have to do in order to figure out whether I can link with it? Well, I have to come up with an ES prime, and I have to show that it is PILS related. Now read this relation as PILS related to my ET prime in order to proceed, okay? And that we've already said is not feasible. The screen keeps going black for some reason. Okay, all right, so I claim, for that reason, we need a new approach that both allows us to handle multipass compilers, verify multipass compilers by verifying one pass at a time, but also allows us to link with target code that comes from anywhere. That doesn't have to be, you don't have to come up with a source language component that is equivalent to this ET prime that someone gave me. And I want to just emphasize one thing here. The problem with this particular problem that I'm trying to point out, okay? Let's focus on this for a second. The issue is not just that PILS or cross-language relations don't allow you to link with code that you cannot express in your language. That is a problem, okay? But you could say, I don't want to link with code that I can't express in my language. To me, the big problem of this approach is that I can't even say what I'm allowed to link with in a source-independent way. You have to bring some source component into the picture. Someone gives you some assembly. You have to somehow cough up a source language component. How are we going to do that? If we wrote the other component ourselves and had the source code for it, great. So basically, what I'm trying to say is, in a sense, what this whole approach is solving is a separate compilation problem. If you have ES and you have ES prime, and you compile them both, either using your compiler, or this approach is relaxing it a little bit, you can go and compile it. Okay, so let's say it this way. If I compile from ES to ET, and I show they're PILS related, because my compiler is verified, it's PILS verified. Now the claim is, I can link with any other ES prime. Suppose you wrote ES prime, and you used a completely different compiler to compile it down to ET prime. Okay? Now what do I need? What else do I need? I have the ES prime, but I still need to know that ES prime is PILS related to ET prime, right? Where's that proof going to come from? You're not going to sit down and do it by hand. So that other compiler better be PILS verified as well, using exactly the same PILS relation. Then you're in business. Okay? So what have we done? We have relaxed the separate compilation requirement ever so slightly. Now I can suddenly link with code, with other code that was compiled from my source language S, right? This ES prime was written in my source language S, and compiled with a different compiler, but that different compiler should have been verified using the exact same PILS relation that I am using for my compiler. So it's not really much of a victory, is what I'm trying to get at, in terms of practically analyzing what the benefit of this theorem is. Yes?
Why does it matter how it was verified? If you have the spec in the source language and you trust it for whatever reason.
Spec in the source language, what does that mean?
So, I mean, you have the definition of the source, and
Yes.
you trust that it's related to whatever the target implementation is.
Right, the word related is the key here. The relationship is being specified by this nice PILS relation, the squiggly symbol in the middle, right? And that is exactly why I say that the other compiler, so for the other compiler, so imagine I have one squiggly arrow for my PILS verified compiler, right? For this compiler, I proved that when ES compiles to ET, ES is PILS related equivalent to ET. Now, I'm asking you to imagine that you have a different compiler that you used to compile ES prime to ET prime. Different compiler, right? Now, in order to link with the output of your compiler, it's a nice thing that you have your source, ES prime, But now, in order for me to link your output with my code, you still have to prove to me that your compiler, when it went from ES prime to ET prime, that you know that you have verified your compiler and you have shown that ES prime is related to ET prime. And not just any kind of related, not a different step index logical relation related. Same relation, same squiggly symbol. That's the only way we can put them together, right? So I'm just trying to sort of get to the bottom line that, you know, this sort of theorem, if we peel away the layers, what the scenario, the practical scenario that the theorem supports is one of, yes, we can link with the output of a different compiler from S to T, but that compiler will also have to be verified with the exact same relation, and that's just not very practical. I don't think we're going to build too many verified compilers for the same source languages to the same target languages, verified with exactly the same pills relations. So that's why I think we need a better approach, right? Okay, so let's talk about a better approach. So we want to handle multipath, and we want to handle linking with things without having to say that we're linking with something that has this particular relationship to my source language, right? That's where we are. So the next two approaches that I'm going to talk about, both compositional CompCert, which took CompCert and, you know, essentially scaled that proof, sort of modified the proof architecture and showed how to do compositional correctness, and this multi-language approach. So before I dive into them, let's step back for a second. I'm going to ask the question from scratch. What is it that we want our compiler correctness theorem to say, right? So I started out with this question of how should this relation between source and target be expressed? But I'm going to go back to this question of, well, what do we want from it? What we really want is what's on the board, on the slide right now. I want, when you give me an ET prime, I want to be able to link with it. Please don't make me come up with an ES prime. Please don't make me show you how it's related to some ES prime. What I want to do is just say that when I link ET with ET prime and I run that, I'm going to see the same observable behavior as when I link ES with the same ET prime and run it. Isn't that what we wish we could do? Essentially what we really would like to have, right?
But doesn't it mean now, like, whatever source languages have to be infected with the semantics of the target?
Bingo. Is that a good thing? Is that a bad thing? And what does infected mean? Is the programmer being shown this? Right? So right now what I'm saying is morally or just intuitively, I claim this is what we would like to be able to say, right? You take that blue and ET prime, put them together, and you put these together, you run them, you get the same behavior. The question of how do we actually do that is the important one, right? Okay, so for starters, let me say that I want this particular relationship to come out of that relation that I'm writing over there. So this is not something that would perhaps genuinely affect a programmer, though I'll take that claim back tomorrow as we talk about it more. But, you know, so this is for the purposes of the compiler correctness theorem. But now, what does it mean to link that purple ET prime with that blue ES, right? You can't just take some target language code and plug it into a source language context or vice versa, right? So essentially what this means, if we sort of follow this idea further, what it means is that you need a semantics of source and target interoperability. And this is exactly the approach that both the compositional CompCert work and the multi-language semantics work has taken, all right? So the way that both of these pieces of work that I had on the last slide address this issue is they do the work of giving you an interoperability semantics between a source language and a target language. They do it in very different styles, as you'll see. Okay, so the compositional CompCert work defines what is called an interaction semantics that is sort of language independent, and it allows different languages, be they source or target, to interoperate. And I'll talk about that in a bit. And then the multi-language approach says, oh, I'm actually going to show you how to define a multi-language between a source language S and a target language T, and so that they can interoperate, so that you can take one of these target language components and literally stick it into the middle of a source language context and vice versa. Okay? But they're both doing interaction between source and target in order to express this statement. Any questions? Yes?
How can you make sure that ET prime doesn't do anything in ES, so it doesn't have access?
Right. So how do you set up these semantics? That's exactly the challenge, right? When we say source-target interoperability, target languages are so evil, right? In assembly code, you can jump anywhere. You can go right into any part of memory. How do we control that kind of access? Especially if our source language is a nice language like ML that gives you nice guarantees about memory safety and so on, and type abstraction, right? Suddenly, if you're going to throw a blob of assembly into the middle of ML, you're not going to have a safe language left over anymore. And that's also a way in which the target language semantics infects the source language in a way that we don't really want. So the moral here is when you set up the source and target interoperability semantics, you have to constrain both languages to behave well, all right? If you're interacting with assembly on one side, if your target language is assembly, that assembly better not be able to overwrite the nice, the parts of memory that are owned by your ML component. Okay? And all of this comes into the picture in both of these approaches. Yes? You can think of it as a protocol. In interaction semantics, it actually is a protocol. Yes. Okay, so let's talk about the interaction semantics approach, which is what compositional ComCert does. So here's a picture from the compositional ComCert paper. Let me walk you through this. Okay, so compositional ComCert has this idea of language-independent linking. Okay, you can take. Actually, before you stare at the picture too much, don't stare at the picture. Or I'll go back. Let's stay here for a second. Okay. So ComCert basically says that if you have, so remember ComCert has languages from C-Lite going all the way down to assembly, right? What compositional ComCert effectively manages to do is say that I'm going to allow interoperation between any of these languages in the ComCert pipeline, okay? So let's just remember that. Now it doesn't literally say any of the languages in the ComCert pipeline, but what it does is it captures the nature of every single language in the ComCert pipeline in a semantic way. Okay? Now, the highest one is C-Lite, the lowest one is assembly. But you know, C is such a nasty language that it's not very far from assembly. That's something to keep in mind, right? So, this idea of compositional ComCert, of language-independent linking, they basically give an interaction semantics which says you can take any languages which satisfy certain properties, have certain semantic behaviors in them, and they're all C-like languages, and you can plug them into what we call our interaction semantics, which allows any code in any one of these languages to interoperate, and they give you a formulation of linking. And then the way that we're going to run these mixed language or language-independent programs now is through these interactions. So they have essentially sort of a transition system. You can be in a running state, and then the difficult thing that they have to model is that while you have one module, one language module, if you will, running, how do you reason about external calls? Because you might make an external call and go to another language. And that other language might have some interference, right? So between that beginning of the external call and after the external call, that other language might do certain things, like write over your memory, you know, the issue that was just brought up. And those would be bad things, right? We want to prevent those. So we want to set up some sort of a protocol which says, okay, I have this interaction semantics, but I want it to be the case that there's some sort of rely guarantee relationship between me, who's running right now, and you, who I'm making the external call to. There are certain things, certain memory things you cannot do, and there are certain memory things I cannot do to your memory. Okay, so basically a whole bunch of rely guarantee kind of relationship between on memory invariant. Okay, and yeah, so there's an initial stage you're running, and the basic task is to how do we formally specify the relationship between this currently running language module and another one that might interfere, and how do we constrain the other one from doing bad things? Yes?
Okay, so now you're talking about memory interference and everything, but we have to have the notion of memory in a source language, right? In L we have lists and numbers, but no memory.
So this is compositional ComCert. We don't know how to scale it to ML. These lectures have a theme. By the time I end tomorrow, I will basically be telling you that compositional compiler verification has tons of work to be done in it. Okay? I have showed you what is the state of the art right now, but they all have flaws. Every single one of them have flaws. And all I'm trying to do is tell you what all of those flaws are so that you can then go and do amazing research and figure out how to come up with the right proof architecture for compositional compiler correctness. Okay. I gave my concluding spiel right now. Yes? They would be useful for this if you're, yes. So if you're trying to think about, yes, absolutely. I'll get to that tomorrow, I think. Yeah. Okay, so, all right, so back to ComCert. I want to call your attention to one thing. So, you know, interaction semantics interface and whatever, but there is a V in here. Which is V is the type of ComCert values, says the very last sentence of this figure caption. V is the type of ComCert values. Remember when I started my first lecture, I told you one of the one of the nice things about ComCert is that the proof architecture is simple. And one of the reasons it's simple is because ComCert uses the exact same memory model across all of the layers of the compiler. Values are represented the same whether you're in C-Lite or assembly or anywhere in between. Okay, this is relying on that in a really heavy way, all right? This is made easier by the fact that they are dealing with the same value representations across all of these languages that they can link together. They all have the same value representations, the same memory model. Okay, so this idea of language independent linking. And the other bit is the structured simulation, which supports the rely guarantee relationship between different languages that I was talking about. And this structured simulation was the hard part. They worked on this for years to try to figure out what are the exact right rely guarantee relationships, these memory constraints that we need to impose on different modules in order to get them to plug together properly. Because if you can't come up with the right invariants, you can't prove vertical compositionality, transitivity. And let me sort of talk about why that's happening. In one layer of the ComCert compiler, they might be doing certain memory transformations across that pass, which are called memory injections. Okay? So in certain passes, memory grows. In other passes, maybe much further down in the compilation pipeline, memory might shrink. Okay? And the weird memory transformations, very different ones for very different passes, but one's happening up here and the other one's happening down here. And what they have to do to come up with the structured simulation is they have to form a mental model of what is happening everywhere. And how do we collapse it into one single abstraction so that every single type of transformation that's happening anywhere in that entire pipeline can be captured as if it's happening in one pass. And we get all the rely guarantee relationships correct, regardless of whether that memory pass is growing or shrinking the memory. Do you see how hard a task that is? Right? You're taking the entire compiler, understanding what optimizations, or rather memory transformations is the important part. You're understanding all of that, and then you are creating a single abstraction in a mechanized way to capture all of them. Okay? I just want to give you a sense of the work that goes into this. And the reason I'm sort of harping on this is because basically you have to do that to get the multi-pass transitivity thing to work out. Okay? What they're really doing is they're going back to single language contextual equivalence. Remember I said they're basically saying, oh, we're language independent. That means we have an abstract model of a single language. And now we're back to sort of a single language contextual equivalence way of thinking about things. And single language contextual equivalence is easy, right? So how did we do it? We took all the languages, collapsed them together, and got transitivity. All right, hold on to that thought. Okay, now, let's talk about drawbacks. So I've already said this. Language independent linking, yes, but this approach works because of ComCert's uniform memory model. Right? Across all of the languages, we have the same value representation. So it's really not clear how you're going to scale this to richer languages, as you've already pointed out, like ML. We just don't know how you might build an interaction semantics that is able to capture, going from one value representation to another. And then the structural simulation approach, I've already just said this. Transitivity relies on compiler passes performing a restricted set of memory transformations. If you come in and you throw in one more pass into your compositional ComCert pipeline, and it does a weird memory transformation that you hadn't thought of before, that is not satisfy the sort of structured simulation requirements, you're out of luck. You're going to have to go redesign your entire rely guarantee protocol in some sense. Yeah.
Say a little bit about what I actually have to do to run this assembly log day with a verified program coming out of this compositional concert. Like,
You mean as a programmer using compositional concert compiler?
well, in terms of like your proof running, right? So it's not like I have to synthesize this ES anymore.
No, you don't have to synthesize. Yes, so that's
You have to say something.
yes. Okay. Absolutely. All right. So you don't have to synthesize ES anymore. You can just give us some assembly, and the only requirement on that other assembly is that it has to satisfy the CompCert memory model. All right. And what that means, if you look at the CompCert memory model, one of the things CompCert memory model requires is that you can't do pointer arithmetic that goes across a block, for example. It's these low-level constraints. But that's the biggest one that sort of jumps to mind. It has to satisfy the CompCert memory model is the only requirement. So what does that mean? That basically means that they can immediately link with any of the languages in the CompCert pipeline, in the CompCert compiler pipeline, because they all satisfy the CompCert memory model. Okay? All right.
I have a question.
Yeah.
What's the expected way that you have some ET prime that you're going to, what's the expected way that you're going to verify that that meets whatever requirements that it needs? Like, is that assuming that you have some other compiler that will generate those requirements and then satisfy them? Or if you just have this arbitrary piece of assembly code, I mean, like, how are you going to know what it does without running it kind of problem before you try to check?
Yeah, so normally you want some way of statically checking that code satisfies certain properties, right? And in this particular case, you would have to know, you would have to maybe build some, I don't know how they actually do this, to be honest, but I presume you could build some sort of tool where you check that it doesn't do pointer arithmetic that goes across blocks or something. I'm not entirely sure. But what I was trying to get at is that requirement, the requirements that ET prime must satisfy in this piece of work are rather simple and can be independently checked. Okay, so you don't have to, yeah. Or if you have code that was written in any of the CompCert languages, then you don't need to do anything else.
Yeah, I'm kind of thinking also the problem, even taking a step back, the whole kind of program
Yeah.
to outside of the concert specifically. Are we kind of hoping that there will be some tool or some compilers that will be providing those static kind of guarantees along the way that then we'll be able to?
I most certainly am in my own research, yes. And that comes back to, so let's talk about the next piece of work, type-preserving compilation. Type-preserving compilation is a way of producing certain static annotations with your target code, right? That says that this target code is sensible, satisfies certain properties. And now if I can just type check that code, then that's my independent checker that I'm okay linking with it. So if we could reduce this idea of, can I link with ET prime to, does ET prime have a certain type that I'm happy with? Then, that's an independent way of checking, yes. Okay. All right, so that leads us to this next approach, the multi-language approach. So the idea here, this is my own work with my student Jamie Perconti, and now there are multiple people in the audience who are actually Dustin and Matt Kolosik right there, who are actually working on follow-up to this. You can talk to them later. All right, so here's the idea of the source target multi-language approach. Basically, specify, so we want to get ES to link with ET prime, and so what we're going to do is specify a source target interoperability semantics. And there was this nice paper on multi-language semantics from 2007 from Jacob Matthews and Robbie Findler. And back then, they basically wrote this paper saying, we don't have nice formal specifications of how languages interoperate. We go out there and we build all these foreign function interfaces for our languages and so on, but we've never properly studied formal semantics of interoperability. So we'll give you a nice formal semantics for how a typed ML-like language, it's basically a simply typed lambda calculus, can interoperate with an untyped scheme-like language. Okay? And the way that they formally set this up, that was the really big contribution, they set it up by, with this idea of language boundaries, which is what I'm going to use here. Okay, so in order to get my source language and my target language to interoperate, I want to specify, I want to take the entire source language, the entire target language, put them together into a single multi-language, and add two new constructs. These constructs are going to be called boundaries. There is an ST boundary, which lets me put a target component, ET, inside a source program, inside a source context. And there is a TS boundary, which lets me put a source program inside a target context, all right? So TS means source inside, ST means target inside, source outside. Okay, so now the interesting part is you have to specify the operational semantics of these boundaries. In other words, when you run one of these boundary wrapped pieces of code, what exactly is going to happen, right? At some point, I'm going to have this source code, and it runs down to a value, and now I'd like to take that value and give it to the other language. How do I do that conversion? That's the interesting bit. Okay, so, but if you can set up this sort of multi-language semantics, then look, I don't have to put, now I can take my ET prime and link it with my ES just by wrapping it in this ST boundary. And I know that, as long as I set up a sensible multi-language semantics. And then, here's what happens. Now, remember, we wanted our compiler correctness theorem to tell us that if we link ET with ET prime, which is on the bottom there, then that should be equivalent to something at the source level, well, or at the top. What is it equivalent to at the top? Well, I take my ES and link it with ST of ET prime. Okay, but now I'll have source on the top and target at the bottom, so I put that whole program at ES with ST ET prime in a TS boundary, so that now I have target code at the top and target code at the bottom. And now it's reduced to a simple contextual equivalence between the multi-language. See, I kind of cheated. I took both languages and I put them into one language so I could get back to my single language contextual equivalence definition. Good? All right. Okay, so we will define compiler correctness then, right? That symbol that we've been trying to define all along. ES is related to ET if ES is contextually equivalent to ST wrapped around ET in the multi-language contextual equivalence. I could also take the boundary and put it on the other side. Instead of putting ST around the ET, I could say TS of ES is contextually equivalent to ET. It doesn't matter which side you put the boundary is just bridging that I'm going from one language to another. Okay? Okay. Now, the nice thing is that this approach, at least conceptually, scales to a multi-pass setting. So I can do this pass by pass. So if I have, again, a compiler from source S to intermediate language I and then to target language T, I can take all of these three languages and put them all together in an SIT multi-language, where basically I define these boundaries that allow me to first go between S and I. Okay, so SI and IS boundaries that go between those two languages. TI and IT boundaries that let me interoperate between the languages in the next pass. All right? And once I've done this, for compiler correctness, what I need to do is, for the pass that goes from S to I need to show that if ES compiles to EI, then ES is contextually equivalent to SI of EI. But the contextual equivalence that I'm using at the top is SIT contextual equivalence. Contextual equivalence for this big multi-language. Okay? And then for the next pass from I to T, I prove that EI is contextually equivalent, again in the SIT contextual equivalence, to IT of ET. All right? So once I've done that, well, that's SIT contextual equivalence, that's SIT contextual equivalence. I'm in a single language contextual equivalence problem, and I get transitivity immediately. And the proof is easy to see. Basically, you have that for the first pass and that for the second. Let's wrap one more boundary around it. And now you see it right away, right? ES is related to SI of EI. SI of EI is related to SIIT, which I write as SIT. So we get the theorem that we want, that ES is contextually equivalent to two boundaries wrapped around the ET. Okay? All right. So you get transitivity. Was there a question? I think a hand went up. Yeah.
Yes.
Yes.
You haven't even responded to this yet.
Yeah.
But I just don't think the back to the prop you're saying from composition of full language components.
Tell me how far back.
Yeah.
More? Here?
Yeah, implies, but the second part of the equation over here requires that your target language has a notion of application.
Yes. So here I just sort of wrote it as application, but I would really like you to read that as linking. Okay. And what I'm sort of abstracting over is how we define that linking, and that has to be sort of language specific. If T is just the target of closure conversion, it can still be application. But if you're at the assembly level, then obviously, you know, it needs to be something else. Okay, so with the multi-language approach, this is how you solve the multi-pass compilation problem. All right. Now, what about the other problem, right? The linking problem. Well, we already talked about that. I don't need this ES prime anymore. I basically can just replace it with SIT of ET prime. I like that. Anyway. Okay. Right. But the point is, so just to reiterate, compositional CompCert and the multi-language approach are both managing to handle linking, the horizontal compositionality problem, in what I believe is a good way, right? Without referring to a source language. You can give me an ET prime and I can sort of independently check whether it's okay to link with it. Okay. What we wanted to do is basically build a compiler from system F to typed assembly language and see whether this approach, you know, how this approach works. Because it's not so easy to just say, I'm going to set up an interoperability semantics between a high-level ML-like language and a low-level assembly, right? The target here is assembly, a typed assembly language. So what we're doing is basically building a type-preserving compiler. By the way, how many people know or have, how many people know about the system F to typed assembly language paper? Okay, I highly recommend you read it. It's a seminal paper. If you're a PL person, you should have read it at some point. Actually, read it and then read it 6 months to a year later again, because you'll get more out of it. Okay, so, but we're basically using that sort of approach for a compiler, building a type-preserving compiler, and verifying each pass at a time using a multi-language approach. So we have 4 languages, F, C, A, and T, and we'd like to be able to do the boundaries and put all of these together in a single language that we call FCAT. And now let's start to sort of zoom in on how we set up these boundaries, okay, and what interoperability means. So whenever we set up these boundaries, notice now I've suddenly put types everywhere, okay? And partly, actually, let me just sort of pause for a second and say, you know, the compositional CompCert work has shown us how to do compositional compilation for a C-like language, right? This problem of how do we do good compositional compiler correctness for type-safe ML-like languages is still very much open, right? There's been so much work on CompCert in that space, but like in the space of how do we do compiler verification, especially for components, for typed languages, it's kind of open. So that's why, you know, we're very much focused on typed languages. Okay, so this is a type-preserving compiler. So when I set up the boundary between F and C, my F language and my C language, I'm going to make sure that if I have an F type on one side, my compiler is going to take an F type tau, and then I'm writing the translation of that type as tau C. Right, yesterday I was writing sigma plus. Instead of the plus, I'm writing C. Okay, so the boundaries are going to mediate between a source language type and the target language translation of that type. So it mediates between a tau and a tau plus, so to speak. Every single layer of boundaries is set up that way to mediate between a type and its translation for that pass. So these translations are the type translations of the compiler. Okay, then how do we set up the operational semantics? The basic idea is, so if we just take a look at the FC and CF language, so if we have the CF boundary E, around E, what we do is we take that blue E and we run it using exactly the source language operational semantics. We run it until we get down to that blue value V, right? So I have CF of E goes down to CF of V. And I've done that part of the running using only the F language, the blue language semantics. But once I have that blue language V, now I need to take it and convert it into the orange language. All right, so I need to take the blue V and convert it to an orange V, right? Like do a translation. And so the hard part, or the interesting part, is how do we actually do that conversion? Okay, and you know, vice versa. But the main idea being evaluate under the boundary using the actual language's semantics and then do a conversion. All right, and you have to set up these multi-language semantics in a sensible way. Not anything you cobble together is going to work. And you need to prove a certain property. You need to have at least this property hold. that if I take a blue language component, I wrap it in a CF boundary and then wrap that in an FC boundary, that better be equivalent to the underlying component, contextually equivalent, right? Observably, wrapping opposite pairs of boundaries around something should not give you code that behaves in a different way. Okay, and if you have that, if you have these properties, you have confidence that you've set up a multi-language semantics that is suitable for being used in your compiler correctness specification.
So,
Yeah.
so I mean, it seems in some sense like there's reversibility here, but this boundary cancellation property is saying, okay, the reversibility is not so strong that you have to get back the same code,
Yes,
but it needs to behave in the same way.
it needs to behave in the same way, exactly. It's as liberal as you can be while still being sensible. Yep. Yeah, this is not syntactic equality. Okay, otherwise we'd need decompilers or something, right? I don't know. Okay, so we have this ESOP 14 paper where we basically tackle the first two passes of this compiler, and we're now working on the final pass and working on various other issues to do with cleaning up multi-language semantics. But let's just sort of do a comparison now, okay, between compositional CompSearch's approach and the multi-language approach, right? So how do they handle transitivity? Well, compositional CompSearch builds the structural simulations. They essentially look at all of the transformations that are happening across the entire compiler and create one abstraction. What does the multi-language approach do? All the passes use the same multi-language. It's the FCAT multi-language or the SIT multi-language. So conceptually, both approaches are doing the same thing, right? They're saying, look, we're not going to get transitivity unless we take all of the languages in the compilation pipeline and put them together. When I put it that way, it's kind of disappointing, right? Or maybe not. Depends on your perspective. Okay. All right, so to get vertical compositionality, both of these existing approaches, and these are the best approaches we have out there to do sort of linking without saying, oh, they are related to my source language in a particular way. They are taking all of the languages of the compiler and putting them together in some way. This is not great. Okay, how does each approach check whether some, yes? Yes? No, actually, I would like to know what you mean by the word simplified, right? Because you could say that I've simplified it or that I've made it harder, and it really is a difference of perspective. Because you win in one way and you lose in another. So let me come back to this in just one point, because I think the next items on my list are actually going to tackle precisely what you're trying to get at. So this slide is about pros and cons of both approaches, right? So the first item, transitivity, I've told you conceptually both approaches are taking all the languages and kind of bringing them into one language so they can get transitivity. All right, how do they check, how does compositional CompSearch check that something is okay to link with? Well, I've already said that ET prime has to satisfy the CompSearch memory model. How do we check that something is okay to link with? We're saying we're building type preserving compilers, so we will only be able to link with an ET prime that is a well-typed and has translation. Okay? But it has to be a translation of the source type. So now that means you need a typed target. You can take this as a good thing or a bad thing. I take it as a good thing. Okay, all right. How do they represent contexts? Compositional CompSearch represents context in a very semantic way. Whereas what we're doing is we have a syntactic representation. We're taking literally the syntax of all of these languages and putting them together in a single multi-language. And again, is that a good thing or a bad thing? From a proof engineering point of view, like if you were going to go and mechanize all of these things, you could say that if putting this many languages into a single multi-language, that's a really heavy thing to do. So to be honest, so the multi-language work has not been mechanized yet, right? So we are sort of comparing apples to oranges. But if you start to mechanize a multi-language approach, we will very quickly see, I think, that we will start to look for proof engineering kinds of things to do where we can create sort of systems for how to deal with more independent languages. How do I mix two arbitrary languages together and I construct sort of a framework and then I give you something where you can plug in different languages, and just to make the proof engineering less work, right? The proof effort viable. So, on the other hand, creating a single semantic representation, they did this for CompCert because CompCert has the same memory model across all the different languages. So you can actually think about it in your head perhaps for a few years and come up with something that captures the appropriate invariance between everything, right? But if you're dealing with ML and assembly, what is the single language abstraction that you could create? Like I will say that I think in some ways compositional CompCert is, I don't know if the word generalization is the right word, but it's a generalization of the multi-language approach. The multi-language approach is saying, let's take all of these languages, syntactically put them all together. The CompCert approach is saying, oh, let's look at all of these languages and kind of conceptually, semantically figure out what all of their power is so that we can have a single language independent thing. Right, so they're abstracting. Abstracting is what you do when you do mechanized proofs, by the way. And that's Andrew Appel's work. I understand how his mind works. We do a lot of that when we do proofs. Yes?
Does the uniform memory model approach give you mutability across the language? It seems like the value.
Sorry, say that again?
Does it give you mutability across like the language matter? So could you like create an object, pass it to the IR or whatever, and have it mutate? It seems like it's something that frequently we do in C, whereas in like systematic language.
Do you want to give ownership of your object to the other language so it can mutate it, or do you want to give it access to a function of yours so that it can use it to mutate it?
Let's say let it mutate.
If you let it mutate, let me think. It's a question of ownership and how sophisticated a type discipline or logic discipline you impose, right? So you've sort of zoomed in on the big thing, right? Different languages own different parts of memory conceptually. We don't want to clobber each other's memory, but we do want to give each other access. So we could go with the total ownership or disjointness model. My memory is my memory. You don't get to write to it. Or we could relax that. This is what the separation logic literature does, right? We have moved from an era of separation logic where separation logic meant disjointness. You specify my memory is disjoint from your memory, and therefore I can reason about it, to an era of like fictional separation logics where, no, we really do need some sharing, but we need to impose good rely guarantee protocols on that sharing so that we can, so that you can tweak my memory without destroying all my invariants. So I'm going to claim that yes, you can do that. No, we haven't done it yet. No one's done it yet. But the tools exist to be able to do it. It's just a matter of specifying much richer, more sophisticated invariants.
But is that dependent on a uniform memory model across the IR?
So the nice thing about the multi-language approach is you don't need a uniform memory model, right? Sorry, was that obvious? No, that's my last point. Okay, right here. Compositional CompCert requires a uniform memory model across all of those, across, anything that interacts. The multi-language approach is allowing an ML-like language, imagine how values are represented, right, to interoperate with closures. Already functions are represented differently, or with assembly language basic blocks, right? Very different memory models. So the nice thing about the multi-language approach is that it is able to scale to different, like just the methodology is such that you can put languages with different memory models together.
So is the first one, all passes use the multi-language context equivalent. Is that just for convenience, or is there a reason why? I mean, it sounds horrible, but for each pair of languages, is it possible to do, a pair of context equivalences that match up, and then for the next pair, another pair?
No. Right now, no, but we have an idea. And I won't tell you what it is, but we have an idea. Okay. So remember I said ES is getting compiled to EI is getting compiled to ET, right? And that transitivity, I can just show you the transitivity slide that I had, right? Because the message is there. All of these contextual squiggly symbols, the subscript on them should be the multi-language, SIT. This is SIT contextual equivalence, right? If I don't use the big entire multi-languages contextual equivalence for every single pass, I don't get this. I don't get transitivity. That's exactly what compositional CompCert is struggling with, right? They don't get transitivity if they don't manage to collapse all of the memory transformations that are happening anywhere in the compiler into one conceptual language independent model. So neither one of us is doing this right, is my claim.
And what would be the simple example to see why you don't get it? One language wants to be one.
Why don't you get it? Oh, yes, okay. So I would put it as horizontal compositionality, which is about linking with code that comes from other things, right? I want to be able to link with some target code. My target language will usually have features that my source language does not have. Now, this is not true of compositional compser because C and assembly are sort of equi-expressive, right? But it's certainly true of the languages that we're dealing with. ML and assembly are not equi-expressive. Assembly can jump all over the place. So it can do a lot more things that I cannot do in my source language, right? Now, horizontal compositionality, which is about linking with code from a possibly more expressive, low-level target language, is at odds with vertical compositionality, which is saying, I'm sitting up here, I'm the source language. There are many, many languages in the middle, and then at the bottom, something that I never knew about might show up. You see how they're at odds semantically? They are completely at odds. You try to get more linking, you have trouble with the multipass issue, with the transitivity issue. You try to get transitivity more easily, you basically have to refuse to link with more things. Okay. Yes.
Just a pie in the sky thing. Like, is it possible to have some kind of higher dimensional relation? Are we talking about I want to relate these logical relations with some higher relations or something like that?
The logical relations across the languages?
Yeah, I don't know, because it seems like if you're trying to unify your contextual equivalents, there's
Yeah.
already some multilanguage contextual equivalents. So whenever you could talk about, well, really there's some other way of relating those different contextual equivalences by some other thing.
Like a meta.
Yeah, like a meta thing. I don't know. Random idea.
Let's talk about it afterwards. Were there other questions? Yes?
So I have sort of a naive thing,
Yeah.
and I want you to tell me why it's stupid. Since what we're worried about is adding more features. Our features are getting worse as we go down.
Yes.
Right? So
Because realistic compilers, right?
yeah. So couldn't we define some sort of we start with some like worst possible language, like untyped lambda calculus, abstract everything to untyped lambda calculus, and then gradually type down into every language that we care about.
It's a great idea. Let's talk about it tomorrow. Because I'll show you something like that. Maybe not untyped lambda calculus, but it's a good idea. Yes.
You would present it with two cases basically, so compiler correctness. Would you actually link programs from different languages together? I mean, if you don't care as much about the code, but I think there's operability between different languages.
So that's exactly what I want to talk about tomorrow. Because I've been saying all of this stuff about linking, and you know, every so often I keep saying, yeah, but I'm ML, and I don't really want to link with this evil assembly code that does things that I can't do in ML. That's sort of what you're alluding to, right? Is it?
I mean, that is not just an abstract proof technique so that you can do an effective proof of compiler correctness,
Yeah.
but actually use it for linking.
And when you say use it for linking, what exactly, what do you have in mind? What use case do you have in mind? Yeah?
And I don't have to first compile them somehow to the same target and then link them with a non-linker, but somehow can take them as they are, more or less. And
Okay, so I'm going to say two things to that. When you say take them as they are, I think what you're saying is I'd like to be able to understand how they interoperate right there at the source level without having to drop down to assembly. Correct? Yes, absolutely agree with you, and tomorrow I will talk about how we want that. All right, number two, I just want to say that at the end of the day, we do want to link them at the assembly level because that's where they run. But we the programmers don't want to have to think at the assembly level to understand how they mix, right? That's the problem. So how do we, this is sort of a segue into how do we build verified compilers that actually give our source programmers better understanding and better reasoning abilities so that they can live in their own source languages and not have to think about what is the compiler doing and how am I linking with this other thing way down in the guts of some assembly language or compiler, right? Yeah.
Somehow, I think what I really mean is, now certain languages have certain foreign function interfaces, but that's all ad hoc. And your approach sounds as if somehow there could be a unified
You're giving my last slides for me right now. I'm going to talk about FFIs, yes. Thank you. That's exactly right. Our language designs are broken. Okay, yes.
To that, 'cause I was wondering, like, because you might have dependencies from an external library that's down at that level. So how do you
lift that up
Yeah.
so that I can think about it at the level of my high-level programming language? That's the language design problem. Go work on it. I'm serious. I'll give you some ideas tomorrow for how you might want to think about it. But it's completely open. Design principled FFIs, please. Okay. I don't know where I'm going next. Oh, these were slides that we've been through. Okay, we have about 20 minutes. Here's what I wanted to do. I wanted to give you a flavor of multi-language semantics. We're going to take our typed closure conversion pass that we did on the board yesterday. And for that pass, this time, instead of setting up cross-language logical relation to prove correctness, we're going to set up a multi-language semantics that allows us to specify correctness. Okay? So this is just to give you a feel for how this is set up. And really, again, the advantage here, and actually let me go back to, one of the things that we showed in our ESOL 14 paper is the following. So we just did 2 passes, but in our language A, we were compiling from system F, which is ML-like but no references, and then closure conversion down to this allocation language. In the allocation language A, we actually put mutable references in there, right? We wanted to say, hey, I, the programmer, I'm working in this language F, which has no mutable references, it has no state. But I'd like to link with a component that does have state, right? This is sort of the dream of multi-language software. I write one component in one language, it has one kind of expressive power, another component in another language because it's able to do more things or different things, right? But I'd like to be able to put them together. And I'd like my compiler correctness theorem to support that scenario, right? So in particular, we show how, we show that the approach is able to handle that. And if you conceptually think about it, it's really very simple. The target language has references in it. But putting the 2 languages together and bringing them into a single multi-language semantics, we are bringing the power of the target language into, in some sense, the full language programs that we will eventually construct, right? So you, the programmer, you're not really any longer writing programs in just your language. You have the expressive power of another language in there, and the multi-language is just sort of making this clear, right? It's being honest about the fact that you are linking with low-level things that don't exist in your language. We do this all the time, right? Our compiler compiles something down to something, to assembly, and then pulls in all of, links with all sorts of bad code that does all sorts of bad things that could never have happened in our source languages. So what the multi-language thing is saying is, well, we have to be, if you're going to do compiler correctness, you have to be honest about the fact that those features are there eventually in your whole program. Otherwise, how are you even going to do optimizations? Okay, so let's jump to the board. So I'm not going to throw more features into the particular target language we had yesterday, because I just want to show you the approach, but I wanted to say that your target could be assembly, it could have jumps, it could have all sorts of things. How do I turn on lights? Are these lights? Oh, lights. We have in our target language. Okay, so I have a source language, I have a target language. I have values and expressions in each language. And what I'm going to do is, basically we're going to take both of these and now combine them together, right? So our starting point is exactly the grammar, the typing rules, everything from the original languages. We're just going to pull them in to our multi-language. All right, now there are a few things to note here. So let's start by saying, oh, I think I need a third color. Do we have a third color? Let's see. Visible? Okay, my multi-language is going to be black, all right? Okay, so I'm going to take my source and target types, and I have to tell you now what are my multi-language types. So this is my ST language. I'm going to use phi for my multi-language types, and basically they're going to be all of the source language types and all of the target language types put together. All sigmas and all taus. Pull them in, pull the grammar in, right? Okay, and we're going to do a similar exercise basically for all the values. So what are all the values of my multi-language? They can be values from my source, or they can be values from my target. Okay, so far that's what I'm doing. And by the way, as these multi-languages get more sophisticated, you might have to throw in more value forms, right? But we won't. This happens when you add references, but today we don't have any languages with references. Okay, how do I take the expressions of the two languages and put them together? Well, I pull in all of the existing expressions, but remember I have to add two new expressions, the boundary forms, ST and TS, which allow me to mediate between them. So what we're going to do is, we should be a little bit more careful here. I'll write it as so I'm going to take my source language blue expression. Now blue is not just going to mean a blue expression that is blue all the way on the inside, right? My blue expressions now might have red inside, as long as it's sitting under a nice boundary. Okay, so my source language can have these terms, ST of E, right? So I'm in the blue language, I hit a boundary, and I cross over to the red. Similarly, on the other side, we're going to say expressions of this language are all the original expressions, but we are going to add a TS boundary that lets us pull in source expressions. Blue is fading. Okay, so now that we've extended the sort of blue and red expressions so that we can vary the other language underneath, under some boundaries, right? We can very easily say that expressions in our multi-language are just expressions from either language, but the important thing to note here is that inside a red expression you might have blue, and inside a blue expression you might have red, sitting under proper boundaries. Now, what I didn't do well is my boundaries have to be indexed by types, okay? So remember I said boundaries always mediate between a type and its translation. Yesterday for type closure conversion, we defined the type translation sigma plus. An int translates to an int. A function sigma 1 or sigma 2 translates into an existential type for a closure. All right, so that's what we're mediating between. These boundaries are always going to mediate between sigma on the source side. I'm just going to write the sigmas in black because otherwise it's going to get too difficult. Sigma on the source side. I'll only put the type on this side, but that means that on the other side, on the T side, my type is a sigma plus, a translation. Okay? So that means that here, this is only going to be well typed if my red expression E has type sigma plus, has some translation type, because then the whole expression has type sigma. Okay? All right. Then we have to appropriately extend evaluation contexts and so on. And I don't know. Maybe I'll skip that part. In the interest of time, I'll skip that part. I will get to the highlights. Okay. Now, remember that judgments, typing judgments in the blue language had the form gamma E:sigma. Right? But our typing judgments in this language had the form delta gamma E:tau. Now our next question is, what is the shape for the typing judgments in the multi-language? How do we bring these elements together? Right? So basically what we're going to do is we're going to say, well, when we type check one of these black expressions right here, that might have some blue or red mixed in on the inside. So it's almost you have to take both typing judgments and kind of bring them together, right? So what we're going to do is notice that blue expressions don't need any deltas. Okay, so I'm going to keep my red delta as it is. So my typing judgment for my multi-language is going to have the shape delta, but now it needs a gamma, right? And gamma needs to contain information about blue term variables as well as red term variables, blue x's and red x's. Okay? So I'm going to extend my grammar for gamma from yesterday. My multi-language gamma, the black one, can contain information about blue x's, or it can contain information about red ones. Okay? All right, so that sets me up for, I have a black gamma. I can type check multi-language expressions, which are the black expressions, which might be blue or red on the inside. And they will have type C. That's the shape of my multi-language type checking judgment. Okay? Now, the way that we're going to pull all of the existing rules from this language into this language is take every single typing rule you had there and put a dot in the place where you need a delta, empty context. Pull all of them in with an empty. No, not pull all of them in with an empty. Pull all of them in with an arbitrary delta there. Is that clear? Sorry, I messed that up. Right? Because now you might find yourself type checking a blue term that has some red stuff sitting inside, and that red stuff might need type variables over there. So just carry around an extra red and an extra typed environment. Okay. So basically take all of these and write down versions of exactly the same rules that look like this, where you don't do anything with the delta, you just pass it around. Okay? Now, what about this one? We pull in all of the typing rules exactly as they are, only change the gamma to black one. Here also change the gamma to a black one, because it's allowed to have both red and blue variables. Now, sorry, that got a bit technical, but let's get to the point, which is, how do we type check the two new expressions that we've added to our language? So we need to be able to type check boundaries, ST and TS. And here's how we do that. One rule. I'm just going to write black delta because there's only one delta. Okay, so under delta gamma, you can have ST with a sigma type here and a red expression underneath. And when does that type check? Well, that thing has blue type sigma if under delta gamma my red E has, you can tell me what it has because I've already said it. What type does it have? Sigma plus. Translation type. Okay? Remember I said boundaries mediate between a type and its translation. And the other rule is utterly unsurprising, it just goes in the opposite direction. So TS, where this E is of type sigma, this has type sigma plus if the blue E has type sigma. I'm sorry, I should have been writing my sigmas in blue, but okay. Good? All right. So nothing terribly surprising has happened yet, right? Yes?
You're gonna need a product type, right? Because you're gonna have to take the unpack back the packs when you're going on your PS sigma, because you need to somehow prove that you have the activity in a categorical sense.
Let's see. Hold that thought. Good thought. The issue what he's thinking about, sorry, what's your name? What he's thinking about is how are we going to put something here, something that might have an existential package type, right, a closure, and then we need to convert it into the source language, but notice the source language doesn't have any products. I think that's the issue. Okay, let's see how we deal with that. So my next task is to tell you how we're going to define the operational semantics of the language. Okay, so the operational semantics, this is just going to be a small step operational semantics. The first thing that I'm going to do is I'm going to, yeah. The first typing rule. Yes, it is requiring, the first typing rule is saying that that red E has a type. In some ways it's saying that it has a red type tau, such that tau is equal to the translation of some sigma. And it's only only when you put red E's under that boundary that have a translation type, for which you know of a sigma, such that red code has type sigma plus, only then is it going to type check. Yes. Now this is a very useful constraint, and it goes back to your point. How are we going to check what code we link with? Basically, we're saying the only code we are ever going to link with is code that has translation type. Right? Because the system is ensuring that that is the only code you can put under an ST boundary. And remember I showed you, we had that ES up there, and I said you give me some ET prime. How do I make them link together? I put an ST boundary around it. But the only target code that I could have put there had to be of translation type. Only then does it get to interact with code on the other side. Now this is actually a very good thing, it's, because this is how you can use types to ensure sensible linking. Principled interoperability, right? This is how I can make sure that I'm not going to link with code that I don't want to link with. I could rig the type translation of the compiler in just such a way so that I can link with certain behaviors when I, if I want, if that's what I want, or not. Okay? You can do a lot with fancy types. But I'll just sort of leave it at that thought, that conceptual thought. Okay, now, let's define the operational semantics. How do we run these boundaries? So remember I said that when I have an ST of a red E, I'm going to run that red E down to a red value V. Okay? So I'm not going to write rules for that. You can do that with evaluation context. Let's look at the actual reduction rules. Once we have gotten that red code down to a boundary, so we have an ST around some red value. Now we have to give our conversion rules. How do we convert red values into blue values? All right? So we have to do these, we have to define the semantics of these boundaries in a type-directed fashion. So if the type over here, the sigma type over here, which should be blue, is int, then that means on this side I have some red value that has type red int. So what is the shape of that value? What red values have type red int? What is the canonical value form for integers? Numbers. N. Okay? That's what I have. Because presumably here I had some red expression E. I ran it using the red language semantics, the operational semantics, as usual. It came down, it reduced down to this particular value. This is well typed, right? I have an N here, that's my assumption. Has to be a translation type of int. Okay, so now I need to take a step and produce something in the blue language. What should I produce? Oh, my blue is running out. Zena, help. another blue. We might survive a little longer. Okay. Good blue, bad blue. All right. Next, let's look at. So I remember I said they're defined in a type indexed way. So the only two types in my source language are int and sigma 1 arrow sigma 2. So we're about to do an interesting case. Maybe the case that you were worried about. Okay, so st sigma 1 arrow sigma 2. Now, I have some red value over here. Let me just write it as that. I have some red value over there. Can you tell me what the type of this value is? It's an existential type, right? It's the translation of a sigma 1 arrow sigma 2. Okay. We need to convert that into a blue value of type sigma 1 arrow sigma 2. Okay. I was going to remind you of something that you've seen in the last couple of weeks. So I need to produce a blue value whose type is sigma 1 arrow sigma 2. Has to be a function, right? A function that takes a sigma 1, and somehow here I have to produce a sigma 2. Yes?
So the unpacking check the context and apply it to the function.
Exactly. This is a package. So we unpack it. What color am I doing it in? I guess. Unpack our red V, and then we project out of the pair. So we take the first projection, which is the code, and we apply it to the second projection, which is the environment. And then, what about the argument? What do I apply it to? X, the blue X? Yes. You're my student. Okay. All right. So we can't just take a blue X and stick it into the middle of red code, right? We have to put a boundary around it. That's the principle here. Whenever you have to mediate between blue and red, you have to stick the appropriate boundary around it. So we've done that. So this is an X. Let's just check. Oh, actually, I have messed up, right? It's an X of type sigma 1. And so this should be a sigma 1. Sorry about the sigma colors. Right? And then we close it off. But now look, I have red code sitting in the middle of blue code. So let's see what's happening. This unpack is going to run our function. The function is a sigma 1 to sigma 2 function. We are giving it a sigma 1 input. So this entire function, when it runs, this thing, is going to produce a translation of sigma 2. Right? So this thing is going to produce something of type sigma 2 plus. But what we wanted to get out from our entire function is a sigma 2. So just convert it. So we say target inside, sigma 2 outside. Okay? Have you seen this in the last 2 weeks? It's exactly like contrasting, and it's exactly like gradual typing. That's the theme that runs through all three things. The idea just comes from higher order contrasts, from Findler and Felaisen's 2002 paper, which said, how do we deal with higher order contrasts, right? You have seen this in contrast. The idea is very simple. Whenever you have a function, you are essentially, doing what we call a contravariant check, putting a boundary in one direction around the argument, and putting a boundary in the other direction around the result. The same theme appears in contrasts, in gradual typing, and in multi-line semantics when you get to the function. Okay? All right. Now, let's do the other two boundaries, and then we'll stop. Of course, okay, so this is easy. When we have a blue int under that boundary, easy case, what do we produce? A red int. And when we have a sigma 1 or a sigma 2 function, what do we need to produce on the other side? Something of type exists alpha and then a pair, right? Okay, so let's see. How do we do that? Basically, we want to produce a pack. Ooh, red. We want to produce a pack. Inside the pack, we need to package the type of the environment. We're back to this question of what is the type of the environment? What is it today? Whatever I like. Today I'm going to put an empty one. I claim that it is perfectly okay for me in my reduction rules for my multi-language semantics to say that my environment will always be empty. Why is that? Because no, not that. I am running programs. I'm giving you an operational semantics. I'm only going to use this operational semantics, or at least right now my assumption is I'm only going to use this operational semantics to run closed programs. And as long as I'm working under that assumption, this is perfectly okay today. It was not okay yesterday because we were in a different setting. We weren't defining an operational semantics. We were specifying a relationship using a logical relation. Right? If we had picked an empty environment yesterday, we would have gotten a much less expressive logical relation. That would have been the wrong thing to do. Today, it's the right thing to do, based on the fact that we're in the middle of running whole programs, which are closed. Okay, so now we have a pack, and then here we have to put some target value that has to be the function. We'll construct it in 1 second, right? This is going to take an environment and its argument and produce some result. And then we package it up with the empty environment because, as I just said, I claim that this code is closed, right? Okay, so what is this red V? That's our last question. Where this V is going to be a function that takes an environment and its argument. Function that takes an environment of what type? Empty, right? Has to be this type. And then, so it takes a red variable of the type sigma 1 plus. What does the body do? Has to produce a... Let's remind ourselves, what type does it have to produce, the body that we try to write with? Has to produce a sigma 2 plus, right? How do we get our sigma 2 plus? We still haven't used the blue V anywhere, right? This function from sigma 1 to sigma 2, now's a good time to use it. Right, so we're going to take our blue V. Blue V wants a sigma 1. We have a sigma 1 plus. So we're going to do an ST with sigma 1 around our red input. Right? I don't know if you can see the blue V anymore. And then we are going to get what output from that? Okay, so then this thing is producing a sigma 2, and we just have to convert it into the sigma 2 plus that we want. Back and forth, right? One direction, the other. Same principle, both sides. And all we did is we just listened to the type translation. We didn't do anything else. The only relevant questions along the way were, what is the type translation of sigma 1 or sigma 2? Let's just use that to figure out what to write down next. Okay, now, I'm going to stop here just with a couple of sentences about what you do next. So this is a multi-language semantics. I've shown you the typing rules. I've shown you almost the entire operational semantics. We just didn't write down the parts about evaluation context. But the key idea is evaluate under a boundary using the semantics of the underlying language and then convert, right? Okay, so we have a full multi-language. This is our ST multi-language. Now, how do we use it to do compiler correctness? Well, the overall theorem is going to be the same. Well, it's the one that we've been seeing on the board. If ES gets closure converted to ET, and this is a typed closure conversion, exactly what we've been doing. ES of type sigma gets closure converted. I'll just write ES and ET now because I don't want to switch colors. then that means that ES, should I switch colors? Oh, never mind. Okay, ES is contextually equivalent in the ST multi-language to an ST boundary wrapped around ET. And on the boundary, I have to put the type. So the ES is of type sigma. So this ES is of type sigma. This should be of sigma plus. And in fact, that is what our typed compiler will produce. So we put a type sigma there, and we say that these have to be related. Now, what do we do with the gamma part? There's something slightly subtle going on here, okay? Which I'm just going to try to hint at. So actually, that is blue. All the variables in the original language that we are compiling are blue. So suppose that there is an x colon sigma sitting over here. Oh, what the hell? Here. What do I do with the variable? What do I put in my environment here? What do I have to do? Good question. Okay, so let's start one bit at a time. Suppose that I give myself the same environment here. What has just happened? Well, I know that when my compiler translates any blue x's in here into this code, it's turning them into red x's of translation type. That's what we did yesterday when we defined our closure conversion path. Remember? Blue x of type sigma gets turned into a red x of type sigma plus. So that is what has just happened. So that means that this blue x that I'm putting over here is perfectly good for this guy, but it's not good for this guy anymore. So what you have to do in order to formally state this right is you have to say, take all the red x's in here, right? Because this can only refer to this right now. There's nothing else for it to refer to. So any red x's that are sitting in here have to be turned into an appropriate statement. So we're going to replace the red x that we know is sitting in here because the compiler turned that blue x into a red x. And we are going to, yes. Let's say this is a sigma prime. This is a sigma prime. Okay? The overall type is still sigma. I just wanted to sort of mention that, right? Just like there's this conversion going on in the opposite direction here, you have to appropriately do that there. All right, so now this is a contextual equivalence. Something that we were talking about yesterday is contextual equivalence is not something you can prove directly. Instead, you construct logical relations to prove contextual equivalences. So now what you need to do in order to carry out that in order to prove this theorem, is you have to construct a logical relation for your multi-language so that you can carry out the proof. And then the proof is just by induction on the structure of the source language derivation, right? Okay. Let's stop there, sorry.